Okay, hope I got everything going right now. What I just did was I just finished doing this whole section with the microphone turned off. And, well, it's not very smart. Okay, we're in section 6.3, Applications of Similarity. This will be the last section we do in this chapter. The next two sections have to do with trigonometry and its applications. And I'm going to assume that you've had that and you remember that. Um, So, be that as it may, once we finish section 6.3, then I'll get into chapter 7 on circles. We have some nice little applications of similar triangles here. These are good things to know. I wish I could ask you to memorize everything, but that's not really necessary in general. What you need to, except for a course like this, uh, what you need to know is whenever you see some of these sorts of figures, you will be talking about similar triangles, and there will be applications. And if you don't remember what they are, you go get your old geometry book and look back at them. Okay, so Theorem 6.9 is the first thing of any importance, the first thing of importance in section 6.3. And the way it reads is kind of odd. In a right triangle, the altitude to the hypotenuse, so I've got a right triangle here, here's the hypotenuse, and this is the altitude, is the mean proportional between the two segments formed by the altitude on the hypotenuse. Okay, to restate that in terms that actually make a little bit of sense, is here's my right triangle drawn. In the right triangle ABC, if it's with the right angle at C, if CD is the altitude to AB, then AD over CD equals CD over BD. This is what the mean proportional is. Okay, is the altitude to the hypotenuse, which is CD, is the means. The AD and BD are the extremes, but CD is the means. It's the mean on this side and that side. Okay, so I'm going to give somewhat not really great proofs today. I might leave a few minimal steps out. I think I'll pretty much say all the reasons. At least you'll be able to reconstruct a really good proof from what I say down here. Okay, first thing, ABC is a right triangle. So the measure of angle A is 90 degrees minus the measure of angle B. Since since triangle ABC has a right angle at C. Okay, let's look at this little triangle up here. Altitudes are perpendicular. So that means that triangle BDC is right angle with angle BDC as the right angle. Hence, look at the relationship between these two angles then. Hence, the measure of angle BCD is 90 degrees minus the measure of angle B. Well, that's the same thing as the measure of angle A. So the measure of angle A is the measure of angle BCD. Okay, well, we had something about similar right triangles, didn't we? Okay. Uh, Triangle ADC is a right triangle. And since I have one acute angle of triangle ADC congruent, whoops, congruent to another, to an acute angle of another right triangle. So this is, what was the name of that theorem? Well, it's by AA. Okay, triangle ADC is similar to triangle, let's see, AD, so CDB. Okay. These two angles are congruent, and those two angles are congruent. I think I have them right, but yeah, I have them in the right order. All right, now by the definition of similar triangles, okay, we know, hence, if we take the ratio AD, which is the long leg of ADC, to CD, the long leg of BDC, is equal to the short leg of ADC to the short leg of BDC, and we're done. Put a little square here because this proof is over. Okay, let's do an example or two. AD equals 8, BD equals 4, find CD. So AD, this is 8, this is 4, and this is what we're after here. Well, the previous theorem tells us how to set up our equation. It said AD is to DC, or CD, okay, as DC is to BD. Okay, probably should call it CD. Yeah, okay. AD is to CD as CD is to BD, because CD is the mean proportional to the two segments formed on the hypotenuse. So plug in everything you know. AD is 8, CD we don't know, CD over 4. Now if you multiply both sides by 4 CD, I'm going to abuse notation a little bit. When I multiply on the left, I have the CDs cancel, I have 4 times 8. When I multiply on the right, the 4's cancel and I have CD times CD. Okay, so 32 is CD squared, square root of 32, which is 16 times 2, which is 4 times the square root of 30, square root of 2, excuse me, is CD. Okay, you can take the square root of the 16, but not the 2, is CD. Okay, number 5. All right, CD is 6. Here. AB is 20. So 20 is the big length here. It's the length all the way from here to there. Okay. We want to find BD, so I'm going to call that little guy X, and that means AD is what's left over when I take 20 and take X off of it. Okay. The equation is the same. AD is to CD as CD is to BD. So let's write down what we're calling everything. AD is 20 minus X, CD is 6. CD is 6, BD is X. And now multiply both sides by 6X to get rid of the denominators. And again, I'm abusing notation. I should write this down on both sides here. But when I multiply the left, the 6's cancel. I have X times 20 minus X. When I multiply 6X times 6 over X, the X's cancel. I have 6 times 6. 20 minus x squared equals 36. Bring everything to the right side. Positive x squared, negative 20x, plus 36. That's 0 is equal to that. Well, this factors. It's x minus 18, x minus 2. Okay, so two possible answers. X minus 18 equals 0. So x equals 18 or x equals 2. X minus 2 equals 0. Now, the way this picture is drawn, the dB would probably be the short side, x equals 2, but there's nothing special about this. This picture may be drawn just terribly inaccurately. So either one of these answers is okay. X could be 18 or x could be 2. All right, let's do some more theorems here. Theorem 610, the side splitting theorem. Now this is not supposed to be funny. Okay, it's not what they mean here. A line parallel to one side of a triangle, so this line is DE, forms a triangle similar to the original and divides the other two sides of the triangle into proportional corresponding segments. Okay, so restatement here in terms of this picture. Okay, there's a line DE which goes through here, and that's supposed to be straight. But in triangle ABC, if DE is parallel to AC, then triangle ABC is similar to triangle DBE, so the big triangle and the little triangle up here are similar. And when we do the ratio, BD, this side to this side, is the same as this side to that side. Okay. So we have two things to prove here. One of them is that the two triangles are similar. So we have to first we need to show this. Okay. So let's start with what we know here. If DE is parallel to AC, okay, so these two are parallel. Well, they're cut by transversal BA. So that means corresponding angles are congruent. Okay. Then angle BDE is congruent to angle A because they are corresponding angles. Corresponding angles formed by parallel lines. Okay, now, what do I know? We know that triangle B, angle B, well, excuse me, what else do I know? I've got this angle up here. Angle right here, DBE is congruent to angle ABC. Why? Well, they're the same angle. They're just two different names for the same angle. Okay. So, since these two angles are the same and these two angles are the same, then we know that triangle BDE is similar to triangle ABC. And this is by the AA similarity theorem. And I believe that has a number 6.4. Okay, so I've done the first thing. Now next, we need to do the proportion. This guy here. So this is the first thing we need to show. This is the second thing we need to show. Okay, So let's go to what we just finished. Since triangle BDE is similar to triangle ABC, we know, and I'm going to turn things over. I'll turn them back over in a minute. We know that BA is to BD as BC is to BE. Okay. So BA is to BD, okay, as BC is to BE. Let me write these two things down again. BA is BD plus DA. That is to BD. As well, BC is BE plus EC is to BE. Now, you can rewrite these fractions a little bit and do some cancellation, but I did that already. Okay. In other words, since this is BD and that's BD, this is BE and this is BE, you could rewrite this as BD over BD plus DA over BD. You could get 1 plus DA over BD. BE over BE is 1 plus EC over BE, and the ones are going to cancel, and you get DA is to BD as EC is to BE. Now, I've already done that, and I did this on page 304, problem number 30. I did that as an example several sections ago. Go back and look at that if you don't follow this. Okay. One more step is to look at this, and we can flip it. If BA over BD is equal to EC over BE, then BD over DA equals BE over EC. And that is by theorem 6.2. They have a number of proportions written down there that are equivalent. If this is true, then this is true, if and only if this is true, and so on and so on. So we're done. We just finished the second part of this. Okay, so side splitting theorem. It's a nice little theorem to remember here. Let's do an example. This is number 14 at the end of the section. Now what they've got here is this picture applies to 7 or 8 different problems. Okay. So there's more here in the picture than we're actually going to use. Okay. BG equals 5, so this is 5. DE equals 15. Okay. Lines with arrows on them, that means that they are parallel. And AD equals 12. So 12 is the big side over here. We want to find BD. Okay, so FC is really not used in this problem at all. Okay, so what does side splitter say? It says that ABC and DBE are congruent. Okay, side splitter says, okay, well actually it says more than that. It says, well, let's do that. Side splitter says that triangle AGB is going to be similar to triangle AED. A line parallel to one side of the triangle forms triangles, similar triangles. So since BG is parallel to DE. Okay, so the little triangle here is similar to that. Okay, and from that we get that BG is to DE, and that is the short base is to the long base as the short right-hand side is to the long right-hand side. Excuse me. AB is to AD. Okay, we can put some numbers in here. BG is 5. DE is 15. AB is, I don't know. AD is 12. Okay, so multiply both sides by 12. When you multiply on the left-hand side by 12, let's see, 12 times 5 is 60, divided by 15 is 4. Multiply the right-hand side by 12, so 12's cancel. AB is 4. And what do we know? We know that AB plus BD equals 12. BD equals 8. Okay, let's do another theorem here. This is the, let me scoot some of this stuff over here. Oh, let's go this over here. Okay. This is the mid-segment theorem, or midline theorem is sometimes called. It says a mid-segment of a triangle is parallel to the third side and half its length. Now, mid-segment is just, if you have some sort of polygon here, the mid-segment is going to be the line that joins two adjacent midpoints. So in this case, the mid-segment of, we have a triangle, whoops, we have a triangle here, ABC, and what I have is D is the midpoint of AB, and E is the midpoint of BC. Okay, so that's what this is. This is and this one says P is midpoint. Okay. If you know that much, then DE and AC are going to be parallel, and DE equals 1/2 of AC. Okay. So now, what I want to show, I want to get some things parallel. So I'm going to need some, like, if I can get this angle and this angle to be congruent, then they would be, I'd have two lines cut by a transversal, corresponding angles congruent. That'd make those two lines parallel. So let's see if I can do that. Okay, first, let's see, here's my proof. First, let's note that if I take that BD is 1/2 of BA, right? Okay. D is the midpoint, so it's halfway. And BE is 1/2 of BC. So if I take BD and divide it by BA, okay, divide both sides by BA, I get 1/2, which is the same thing if I take BE and divide it by BC. So the ratio of this short side to the long side here is the same thing as the ratio of this short side to this long side. Okay. Also, angle DBE is congruent to angle ABC. That's true because they're the same angle. And the reflexive property is when something's congruent to itself. Okay, so I have some sides in proportion. I have a left side in proportion, a right side in proportion, and the angle in the middle is congruent. So that is by side angle side similarity, which is 6.6. Okay, triangle ABC is similar to triangle DBE. Okay. And this means two things. Okay. First off, it means that corresponding angles are congruent. Angle BAC is congruent to angle BDE. Okay, BDE, BAC. Okay. So this means DE is parallel to AC because congruent corresponding angles force parallel lines. Okay. Also, there should be a capital A here if I can write it. Also, since triangle ABC is congruent to triangle DBE, then sides are in proportion. In particular, the short base divided by the long base. So DE divided by AC is going to be the same as the short side on the right, on the left, excuse me, BD divided by BA. But BD divided by BA is 1/2. So DE over AC equals 1/2. Multiply both sides by AC. DE is 1/2 AC. Okay, so connect up the two midpoints. You're going to have parallel sides. You'll get similar triangles, and the bases here, these two parallel sides are going to be in the same proportion as everything else, 1/2. Okay, nice little theorem there. Here's a big corollary, really important thing, which is very, very simple, but it seems to me to be like an amazing result. Take any quadrilateral. I mean, any quadrilateral. It can be really, really awful looking, and I'm going to draw one crazy one here in a little bit and show you that it still works. So take any old quadrilateral. I wish they'd drawn something even screwier looking than this, and then let E, F, G, H be the midpoints of the sides. So E is the midpoint of AB, F is the midpoint of BC, G of CD, and H of AD. Okay. Then if you connect the midpoints in order, you get a parallelogram. Now that seems to me to be a remarkable result. Okay. But it's pretty easy. So here's the statement, here's the restatement based on this picture. Okay. And the proof is real simple. I'm going to go through this rather quickly. Well, let's do green here. Okay. So the first step is to draw AC. This is a real quick proof. I'm going to go leave some steps out here. Okay. Then use the mid segment theorem on, we do it on triangle A, ADG, DC, excuse me, to get that HG is parallel to AC. Let's work up here now. Use a mid-segment theorem on triangle ABC to get that, okay, that EF is parallel to AC. Now, we already had that HG was parallel to AC. So, if HG is parallel to AC and EF is parallel to AC, hence HG is parallel to EF. Okay, hold on to that. Now, make sure I got the right color here. Okay. Now, draw BD. Okay. Mid-segment theorem says that HE is parallel to BD, and that so is GF. So HE is parallel to GF. Okay, well, if HG and EF are parallel and HE and GF are parallel, so therefore here's parallelogram. Okay, so a nice little corollary. It gives me a really, to me, it's an amazing result. Okay. Yeah. So let's see if I can draw a really screwy. Yeah, I'll do a little better job than that. See if I can draw a really screwy quadrilateral here. Okay. Now this isn't going to look real good because I'm going to estimate it, but here's one midpoint, here's another, here's one midpoint, here's another. If you connect these, and I can't connect them worth a darn on this, you connect these and connect these. Ah, stupid thing. Why does it stop? Connect these, connect these, connect these. You get a parallelogram. Even if your original quadrilateral is a really goofy quadrilateral. It's amazing, amazing. Okay, let's do two more problems, one more computation and then one more proof here. In parallelogram PQRS, A, B, C, and D are midpoints of the sides. So I know that this and that are the same. Now, since the opposite sides are congruent here, it's a parallelogram. I know that this and these are the same as those. this and this are the same, this and this are the same as are these two. Okay, now ABCD, if the area of ABQ is 5 square inches, so that means this is 5. Okay, find the area of the hexagon, P to A to B to R to C to D. I'm going to draw some lines here. Let's pick a different color. Yeah. Okay. Let's draw the line connecting B and D. Okay. Now, what do we know about that? Well, we know that it is parallel to RS and to QA. Let's draw the line connecting A and C. We know that it is parallel to QR and to PS. Now, one of the other, okay, let's go ahead and draw, let's draw the line connecting P and R. We know it's parallel to AB. What do we have here? We have a whole bunch of little triangles that are all the same size. They're all congruent to each other because I have angles. This angle and this angle are the same. These two sides are the same. Those are the same. This angle, this, okay, this, this. Anyway, what I'm trying to say is all these little triangles are congruent to AQB, so they all have area 5. There's 6 of them, area 5, each 30 square inches. Okay, one last problem. This is a proof, and I'm probably not going to do this one perfectly either. I'm going to talk more than I write down. We want to prove that the midpoint of the hypotenuse of a right triangle is equidistant from its vertices. So this is what the statement here on number 27 is. So the first thing is to draw a decent picture. So we're going to assume the triangle ACB is right with angle C being the right angle, and that D is the midpoint of hypotenuse AB. Okay. So we want to prove that the distance from D to vertex A is the same as the distance from D to vertex B is the same as the distance from D to vertex C. And the proof, dA equals dB, because D is the midpoint. Okay, that's easy because that's free because of our assumption here. Okay, and what we want to do is to do something about this guy. We want to show that DC is the same as DB. Okay, so now we need to do a little bit of construction here. Let E be the midpoint of BC. Okay, so it's going to be about here somewhere. Okay, and let me draw in this line. All right. use a mid-segment theorem, okay, to say that that should be E. I didn't label it here. DE is parallel to AC, so angle DEC is congruent to angle, let me back up here, DE is parallel to AC, so the measure of angle DEC is a measure of angle DEB is 90 degrees. So these are right angles. BE is congruent to CE because E was the midpoint, and DE, DE is congruent to itself because of reflexive property. Okay, so I have, what have I got here? I've got leg and leg. Hence, triangle DEC is congruent to triangle DEB. Leg, leg. So side DC is the same as side DB. So we're done now. Hence, DA equals DB. Whoops. DA equals DB equals DC. Put a box here, which means my proof is done. And we're done. Well, I hope this this helps you on this section. I will post some. I'll post this later on this this evening. This is Monday the 26th, and I'll post the homework to go along with this. I'll get section 7.1 done and post that sort of thing tomorrow, and see if I can't get myself caught up on everything. I've gotten a bit behind because I've been worried about other classes, and hopefully you're off to a good start in whatever Module 4 classes you've got this term. Good luck.